think recording. All right, guys. So let's get started. Okay, so let's get started. Welcome back from your break. All right, a couple of reminders. Currently, we are in week 11. Week 12 is what? Exam 2, right? So next Tuesday, you have your exam 2, which is going to be similar to exam 1. It is comprehensive. It'll cover everything from week 1 all the way to what we cover this week. You're allowed, it's closed notes, but you're allowed your cheat sheet. So an 8.5 by 11, you can write whatever you want on it. Questions? Yeah. All right. So don't forget the exam on Tuesday. Yeah. You won't be. Yeah. You had mentioned the exam, right? Yeah. So I'll have to give you a makeup exam of some kind. Yeah. Just send me an email about it. Any other questions? Any other issues? All right. So don't forget that exam this week. So we're currently on week 11. Oh yeah. Yes. 372 is also on Tuesday. All right. Yes. So the exams are scheduled. You've also started to work on your term project, hopefully. So that remember that's something that is ongoing. This week I'm going to introduce, should be a nice topic. So I think one thing I'm doing in this class is I kind of give you some of the foundations, but also like throwing you some of the heavy stuff, right? And so that way you're not just stuck in foundations, you can also do stuff. That's kind of the idea. So we've been covering a lot of foundations in the past, and then we're going to gradient descent. So you have to read a paper. It's somewhere. I'll show you where it is on the GitHub, and I want you to start reading that as your home reading assignment. But this week, we're going to cover the CIFAR10 data set. It's like MNIST, but the advantage of CIFAR10 is in color, whereas MNIST is in black and grayscale. And so that makes it more challenging, right? And then you will have a homework assignment this week, which is a bit more challenging, but should be rewarding in the sense that once you do that, you have something pretty good. So we're going to take a look at that. So before I forget, I guess, let me do the GitHub, the paper. I want you to start just reading this paper. It'll motivate a lot of what we're going to do. So if you go, you should be seeing the GitHub. And if you just go to the foundations repo, right? And I've provided here, go to the neural nets, and then should be under neural nets. So we've talked about a lot of this, I think, but I provided this paper, the Rumelhart, Hinton, and Williams paper from 1986. Don't worry, it's a short read, actually, surprisingly. It's very short for such a fundamental paper. Here's the Toronto link. Notice in particular, it was published in Nature. So Nature and Science are like, you have to discover like what is a black hole. You know what I mean? Like it's got to be something very significant. So it tells you the importance of this paper. So it's in Nature Notes, I think it was. And if I click on this one, this takes us to the University of Toronto website. And it's actually like they just so old that they just photocopied, I think, this thing. But here it is, learning representations by backpropagation errors. This is literally one of the most fundamental papers. It's what makes all of this possible. So how do you already know how to train a simple neural net, right? That's what we learned the other day. What was that called? The perceptron. Remember that approach? And so that's what you know. So imagine you're in 1984 and you're very versed in the perceptron and you're all excited about it. And then all of a sudden it's 86 and you get this paper. And it takes you forward. You know what I mean? It's like, so that's what I want you to read through. We'll discuss this idea. So you can see the papers there. It's very short. It's only like 3 pages, I think. And it ends like when you see this line, that's totally different paper. I think this one is from the Department of Psychology, so it's not even related. Okay, so this is your reading assignment. Okay, so just kind of start reading through this one. Should be a nice read. Very important though, and fundamental on how we go from the perceptron to what we have. This is about stochastic gradient descent, basically. It's just the technique, most formally known as backprop or backpropagation. Okay. So everyone know where this is, right? So just go, it's free, print it. It's like 3-4 pages, and start reading through it. It's an okay read. All right. So that's one thing I wanted to talk about. So now we can go back. Yeah, let me just switch quickly to the PC. Yeah. So I've also updated the Brightspace environment. So in the Brightspace environment, as you can see, we pretty much cover all of this, right? So we've gone through all this. I believe this was the last thing we covered last week before spring break. And now this is what we're covering this week: CIFAR10, DNNs, and CNNs. So I'm doing something similar to what I did with XOR. Remember in XOR how we did, what did we do there? We did a linear classifier, right? And we couldn't solve it. And then what did we add? We added deep learning, right? And we were able to solve it. Do you remember that? Well, in CIFAR10, we're taking it, you're going up in time again to about 2012, right? And so now you have DNNs, you have CIFAR10, and you're going to try to solve it with the DNNs that you have from XOR. But as expected, you will not be able to get the accuracies that you get. And then we're going to throw at it something called a CNN, which is the convolutional neural network. And maybe you've heard of it, maybe you haven't, but it's definitely more powerful. It's, there's deep learning, and then there's the advanced. There's like three really advanced deep learning algorithms called transformers, CNNs, and basically GANs maybe. We're not going to cover these in a lot of depth because this is, but, as I said, this is where I'm giving you some of the, powerful tools to tackle problems. Okay. And the scenario will be, oh, sorry, I need to switch back. So the link is here, right? And this just takes you to the GitHub. And you will have a homework assignment. So I'm going to go back then to the foundation. So it should be under TensorFlow. Yeah. And yeah, CIFAR10. So we're going to go over this one. And this will be the, for this week, basically the focus. We're going to go through the code and everything, code it up, and I'll explain it. But basically, you can think of it as I was saying, in XOR, we went from linear to deep learning, and we, advanced quite a bit. But now deep learning, right? Because this is the thing that you've probably been using. And now I give you some images in color. So I think it's 60,000 images for training, 10,000 for testing. And I asked you to, compete, right? And see who wins. And so most of you will throw at it what you know, which is DNNs, right? What you have from CIFAR10, and you will not be very successful. But then if you throw CNNs at it, boom, you go up. All right, so obviously there's a lot there. I need to kind of, in an intuitive way, discuss what a CNN is. And so we'll talk about that and how it's a little bit different from deep learning in general. And hopefully that'll make sense. Questions? All right, so that's the plan. It's important that you keep in mind what the homework assignment will be. As you probably can imagine, CIFAR10 is a set of images. It's a data set of images. So we're exploring the classic thing that people have studied for many years. So people study either natural language processing, text, right? Or they explore image processing, right? Those have been the two mediums. And that makes sense because that's what the big companies like Facebook, Google, they have a lot of media. And the media was, social media, whereas you guys post text or you post images, right? And that's what they've had a lot of over the years. All right, so so that's the plan, to explore CIFAR10. The homework assignment, as I was saying, it's really important that because I'm gonna solve the code, but I'm not solving everything. So there's a bit of a challenge in your homework assignment this time around. So we'll be using CIFAR10. Imagine it's color images. I think they're 32 by 32, right? For your homework assignment, you will need to find an image data set in color that's large, some other one beyond CIFAR10, right? So you need to download those images, and the code that I'm providing loads the images from a library. Very conveniently, we just use like a standard Keras library. But what I want you guys to do is to download your images into like a folder in your computer. And your challenge will be to take those images and convert them into tensors that fit into CNNs. This is an important thing because a lot of the time, this is what you have to do. It's kind of what I'm highlighting here is that you already have a CNN after this week, right? And you can apply that CNN to every problem. But what's going to change is your images. Next time around, you're just going to have some set of images you never thought about. And so you need to be able to grab the images and create your X and Y, basically. Remember the X and Y? That part I can help you out, obviously, but I will leave that part to you. Got it? I will give you some recommendations, though, of how you should approach that. And basically, this is a classification problem. So I think CIFAR10, as the 10 implies, it's got 10 labels. So this time around, it's cats, dogs, bus, bear, something like that, right? So those are the types of classes. Your problem also needs to be multi-class, which means there's binary and multi-class. So binary, there's 2 classes. Multi-class, 3 or more. So your problem, whatever your color images are, they need to have at least 3 classes. And usually the best way to do this is to assign the labels to images is to create a folder per class. You see what I'm saying? So when you download your data set, let's say that you have 4 classes, right? Let's say it's fruits. So apple, orange, banana, grapes. You have 4 fruits. So you'll have the names of the files will be apple 1, apple 2, apple 3, something like that. You could get the label from the name of the file, but it's usually a very common and standard approach that you put the name of the class in the folder. So it'll be 4 folders of apples, of bananas, grapes, whatever the other thing I said was. Do you see what I'm saying? And then if you do that in the future, when you start to encounter a whole bunch of libraries, what you will notice is everything works because it's all made kind of like that. See what I'm saying? But you can get your labels. And I mean, you could have a text file with the labels and the name of the file and map it somehow. I mean, there's a lot of solutions, right? And when I have in set, the students come up with 100 different solutions on how to do that. So my recommendation, folders. Folders, the name of the folder is the name of the class, and then your images are in it. Got it? All right. The other challenge is you're going to deploy this to GitHub. What does that mean? There's another challenge there, right? Because you're going to have to, from the website, click a button, load the image to the website. Remember that what happens there is that you have JavaScript, right? TensorFlow.js. So what does TensorFlow.js have to do? It has to take that image, convert it into a tensor. So remember, think in terms of it's going into a neural net, so it needs to be converted into a tensor. Now you're only doing inference on the website, on the deployed GitHub. So you only need one image, right? I'm not asking you to do like a folder of 100 images and run them at once. Probably not a good idea because of memory. It's just enough to load one and do the inference on the website. So you're going to deploy it as well. Deploy the CNN. Now, the only issue, I haven't thought about this one. If I don't think the model is that big, but remember, GitHub has a 25 MB limit, right? So hopefully that won't be an issue. Otherwise, you'd have to do it locally. Wouldn't be as fun. But does that make sense, guys? That's the homework. All right, so that's the homework. You can literally start working on it right now if you want. But basically, that's what it is. You're going to download some images. As I said, today, if I was just thinking in terms of foundations, we were at the perceptron and foundations. Now I'm jumping a lot, right, to CNNs. What I want to stress is it's not that I'm skipping all of this. We're going to come back to gradient descent, but it can take a very long time to get to something. And then it's like 2 weeks till the end of the semester when I'm actually showing you this code. And so I feel it's better if I show it to you now so you guys can maybe consider this for your project, if that makes sense. All right. So yeah, so we'll do that today. Yeah, and that's it. So that's the homework. Of course, I'll write something on the right space, but that should be the basic idea. Questions? Make sense? Yeah. The other thing is just a comment. So, I've been doing machine learning for a few years, and it's been crazy the last few months. I don't know if you guys see all the hype, but it's been astonishing to me. I don't worry so much about like, is it sentient or not? That's not really what I'm concerned about, but I am amazed at the fact that these tools can do what they can do now. It's not a question of, is it going to wipe us all out or something? It's a question of these tools are really doing some amazing things. So definitely, I want to show you guys something just to kind of motivate you. This is not ChatGPT related, but it's something pretty cool, I think. And I think you'll appreciate it. So this is something I'm doing with my grad students in the other class. I think it was here. Yeah, it's here. So this is called art style transfer. So this is not even CNNs. This is beyond CNNs. You know what I mean? So hopefully you guys see that you're still at the perceptron. And then there's deep neural nets or multi-layer perceptron, then deep neural nets. Today, we're talking CNNs, but on top of CNNs, there's something called transfer learning, which is something you don't know about. And on top of that, there's this thing called GANs, generative adversarial neural networks. Beyond that, there's something called art style transfer. And this I thought was pretty nice. So this is, like I said, the students were doing this. So what this does is I can transfer the style of one image to another image. So for instance, let's say that you have a picture and you've always wanted to make that picture into a Vincent van Gogh, like if Vincent van Gogh had painted it, or Picasso, or Monet, or something like that. So that's what this does. Gaddy's neural style transfer is an algorithm. I think it's from 2018. You can take a look at the paper there. So here's all the code. Anyway, that's kind of, that's a Picasso, right? And then this is Ballerina, and you do all the processing, and now you have a Picasso painted Ballerina, right? Now we did this we got a Monet. This is water lilies or something like that. And we got a picture of the university, Purdue University Northwest is one of the pictures here. And we did the style transfer for just a few artists. And this is the rendering as a Monet, right? And then Vincent van Gogh, you guys are familiar with this one. What is this called? Huh? Starry Night. Starry Night. And so let's see what it does. There it is. I thought that was very good, actually. If you look at the stroke of like a painter, if you look at it, look, it's like it was painted over. So I thought that was pretty nice. And then Picasso is actually, I was surprised at this because it's a really dark painting. But if you look at it, it also came out a little darker, but still pretty interesting. See? And my point is, in telling you this, I'm not saying this is sentient or we have to worry about it being sentient, but it is a very powerful tool. Whereas these things were toys before, and this would have been like random and blocky, and this is actually good. And this is not, by the way, something called stable diffusion. Maybe you've heard of stable diffusion. Stable diffusion is even better than this, okay? And also this model that I'm using is and this is kind of another thing I want to mention. There's a thing called transfer learning nowadays. And what transfer learning means is that you train a model, right? And the weights of the model can now be used later. You see, it's like you create this pipeline that can do certain things with the pre-trained data, but you can add on like other layers at the end. So you don't have to train, if let's say there's 100 layers, you already get 90 layers trained already, and you only train the last 10 or less. What's the advantage of that? Well, the advantage of that is that, for instance, for this example, for this to work, right, this style transfer, I had to use something called the VGG model. So that should be in here somewhere, I think. I think it's there. I have the beginning one. There it is. Download VGG. You see that? VGG pre-trained model. Just one line of code. That's it. One line of code. This probably took maybe $1 million or so to train on some very powerful supercomputers with GPUs, maybe 10 GPUs, millions of images. Okay, I believe VGG is what came second to ResNet. So in CNNs, there's two main CNNs. So I'm teaching you today just plain vanilla CNN. We're going to code it from scratch, but it's not pre-trained. What does that mean? It means that the weights are initially what? Random, right? You guys agree with that? Whereas for me to do this, and apply neural style transfer, I couldn't just do it from scratch. You see what I'm saying? So I'm leveraging something called the VGG. And the VGG is, as I said, there was a competition where they said, create CNNs and let's see which one wins. And I believe ResNet, it's a version of a CNN with specific architecture. I think it has 156 layers, right? Today we're going to do a CNN of 2, I think. That one has 156. ResNet 50 or something. VGG, if I remember correctly, came in second, okay, to ResNet. But you can see here from models, I'm using, I think it's PyTorch. I'm using VGG 19 and I'm loading it from somewhere. But what that means is, I don't remember the number of layers, but let's say it has 150 layers, right? I'm loading those 150 layers, but I already have the weights. You see what I'm saying? I already have these weights and I'm just using them. And then maybe I'm adding two more layers at the end, which are what I train on this problem of neural style transfer. So with the CNN that I'm giving you for CIFAR10, you probably could never do this, right? You probably could never accomplish this kind of, this kind of effect to make anything into a Monet. And what's great about this is any Monet, not just Monet, but any Monet or any Van Gogh or whatever your favorite painter is, or maybe a theme of the West or Star Wars. I don't know, whatever look you want, it can be transferred to any other picture. I think the only condition is that the images have to be the same size. So you have to kind of do that. But I mean, that's just, So anyway, you couldn't do this with the CNN I'm giving you because, first of all, too small. That's the reality of it. You need bigger and bigger models, which means you need more computing power. You need more data, right? And so but then that created this paradigm or whatever that you have pre-trained models, right? So here we bring in that VGG and we bring in those weights and are able then to accomplish such things. Got it? Does that make sense? All right, so that's an important note for you to understand, I think. All right, so this is vision processing. And the idea with the 150 layers basically is that you showed that model of 150 layers, probably 10 million images. And you told it, these images are cats, these images are dogs, whatever. So eventually it started to learn in the network how whenever it sees, like, maybe here it recognized letters, and here it recognized leaves, and here it recognized grass. And it starts to create a neural network that can, from one layer to the next, to the next, to the next, can understand more and more and more of what it's seeing. In a sense, it's creating features. You see what I'm saying? So it's like you have the original pixel features, but from that, the next layer combines some pixels to understand, you know what, these pixels look like they're making a line. And then in the next layer, these lines, you know what, they're making up a curve. And in the next one, hey, you know what, these curves are actually making a circle or a triangle. And then these circles are making eyes and so on. And then here's a face. You see what I'm saying? So this is kind of how it's doing. And then you just take that architecture, which essentially you give it an image. By the time it gets to the 150th layer, it found the eyes, it found the grass, it found the letters for any image that you give it. Does that intuition work for you guys? Why this is useful? So the power of this is that you get things that can process an image and convert it into a whole bunch of other images, if that makes sense. Right? All right, that kind of also leads us into the idea of CNNs, right? So now I'm done with my whole transfer learning thing, all right? Now we're going to go back to the very, very beginning. No pre-trained model. You're at a deep DNN, deep learning algorithm. Now you're scaling up a little bit to a CNN, and you want to know, so what is the difference, right? What is the difference between a DNN and a CNN, right? So any questions before I move on? Nope. And I think I was recording all of this, right? How do I know that? Yeah, it's recording. Okay. All right, so we're going to go back here. Now I'm going to show you. I won't go through this script, but I recommend that you play with it at home. All right, this is just something that is kind of to motivate how CNNs work. All right, so I'm going to go over here. We're going to go to the repo. And we're going to go to the foundations link. So CNNs, right? Go to neural nets. So there's a couple of ways to think about CNNs. One way is they're going to give you all the equations, right? And you can know all the math and everything, but I'm pretty sure you're still going to be missing the intuition of it. So let me show you this approach. All right, so this is NN's math, right? Where I have all this stuff, the dot product and everything. I added a new Jupyter here called maths convolutions, right? And I just want to give you the intuition as to what is going on in the CNN. So this is pretty simple. It's not really, TensorFlow, or it's not even written in matrix multiplications. I think this is pure for loops. So obviously it is not efficient. But I'll tell you kind of what happened in the past. So maybe 15 years ago, probably, this is what people used to do. People would take an image, any image, and they would run it through several filters, right? So they had several filters. So what are some filters that you can run on an image? You can blur an image, right? Why would blurring an image help? I don't know, but you could. That's a filter. You could also find what is called edges, right? Which means you filter out some things and you get edge detection, right? And that was the pipeline. So if I was 15 years ago doing this, I would have done, okay, I'm going to take my image. I need to find all the good filters that are out there. So edge detection, something called wavelet transfers. What else? What's another good filter? High pass filters, low pass filters, averaging filter. You know where I'm going with this. So I have to literally make a list of all the filters that people have created manually that take an image and process it, and you get another image. Same image, but processed, right? And then what do you have now? What you have now is the original image plus the same image, but run through all these filters. Now your vector gets much bigger, right? You agree with that? But at the same time, because you processed it with filters, you have more information. Like the advantage of a filter is in an edge detection is it got rid of some information. You see that? So that the neural net or the machine learning algorithm, because this is not even dependent on neural nets anymore, can just focus on the filtered image. You see what I'm saying? But this was problematic because maybe it took a person 4 years to invent a new filter. Humans aren't actually great at this, right? And so that was the issue, right? That you had to invent the filters, you run the images through the filter, and then now you had a vector that was the size of the original image times the number of filters. That was your input to the whatever step, maybe KNN, or whatever, any algorithm that we looked at, or neural nets also. And then you do the classification. Do you see what I'm saying? This is what we used to do. CNNs changed that approach. And instead, what they said is, yes, that's a good idea, but let's not manually create these filters. Instead, we're going to let the computer figure out these filters. Do you guys see that? That's much better. Because the computer does what? It's going to find new filters that humans would have never discovered. And it finds new filters for every different problem. And that's what a CNN basically is. Okay, when you hear this idea of a convolution, what is happening is you take an image and you're running a filter through it and producing another image. Here I have some examples. So like I said, when I was studying, I had to take a couple of image processing courses, and I can tell you they were not my favorite classes. All right, it's a lot of pure algorithms of processing images, right? And these are written in for loops. So, one of the reasons why I chose this is because it's intuitive for you guys can really understand. If you're curious about how this works, go ahead. It won't be on the exam, but if you're curious of just, running a few filters through an image, go ahead, okay? Now this should work fine. So here's the example. So of the intuition of what a convolution is, right? So the CNN is running filters through the image to produce filtered images. So you started with one image and you have 10 filters, you end up with 10 versions of that image. But because we are using tensors, that's not a problem, right? Because we have 32 by 32 by 1. Now we have 32 by 32 by 10. You see that? Does that make sense? It's a tensor. We can have tensors of any dimension. Now we have color RGB, but that's also not a problem. We apply to every color, every channel is called the 10 filters. Got it? Any questions about that idea? All right, so this is the code. If you want to play with it, just use this SK image. This is just sklearn for images. And basically, this is the original image, right? So low res image, and to keep it simple, it's black and white, because imagine if you have to do this for loops for 3 dimensions. Probably not fun. Also, it kind of underscores the fact that I don't encourage you to learn to do this manually. Feel, in fact, lucky that you don't have to do this. All right, so here's one filter. This is the horizontal edge filter. So this is important, and pay attention to this. See that? Those numbers there? A human came up with these, right? They had to brag that they're pretty smart that they came up with it. You know what I mean? It's literally that kind of thing. So it's like innovation. The more complex a filter was, or the algorithm, because it produced something valuable, that's, hey, give them a PhD, right? So that's kind of the idea. So this is then, these filters were manually processed. And there's a lot of filters, and I'm not saying bad things about using filters, right? I mean, obviously they are used quite extensively in electronics and electrical engineering. I'm just saying for image processing and for machine learning, it wasn't very practical. And CNNs changed it. How do CNNs change this? when a CNN, not the VGG, because the VGG that I showed you for that transfer learning thing with the Monets already has these values, but also other filters that possibly humans have never even imagined existed, right? Because what it does is that it finds these. Just like we find the weights in a neural network, a convolution is a matrix multiplication. So it falls within that same idea of X times W, which means the filter is basically, you can think of it as the W in this case, which means it's what? It's the weights. So basically the same procedure allows us to learn the weights. You see that? So in a CNN, when you're starting it, you define that you want all these filters, but these values are initialized to what? Random values, probably. Probably don't want to initialize them to zeros or ones. You initialize them randomly. But as you start giving it data, it learns these. And the more layers it has, the more it can take one image that it processed to produce another image and use that to learn another filter. And you know what I mean? So it actually learns filters on top of filters on top of filters on top of filters. Okay, so today we'll do not today maybe, but this week we'll do a CNN of 2 layers. So we'll go over the convolutional layers. Luckily for us, we're using Keras. So Keras allows us to abstract this to such a way that it's pretty easy to set up, okay? But that's kind of where it's coming from. So, like I said, the best intuition, I think, for you to understand how CNNs work is to think of it this way. So here, traditionally, this is before, I don't know, let's say 2007, sometime like there. You take initially, your pipeline would have been, take this image, run it through however many filters you have. So here you can see I have a horizontal edge filter. A human already came up with these weights, do all the very exciting for loops there, and do all the operations. So, and then look, the image gets filtered. You see, it's no longer the same original image. You see that? And this is a horizontal edge filter. It's focusing on that type of edge because of these operations that are being applied on every pixel in the original image. Because you're going like this. Imagine it's like you're like scanning the image, the original image with this filter, and converting things into a new pixel representation. Then I have another one called the vertical edge filter, and you can see this has a different way the values are arranged in this filter. Do you see that? And when you do all the great for loops there, now you have a slightly but different version of the image. You see that? But now we have the original image and the horizontal and vertical. So we got 3 versions of the image. Do you see that? Okay. And then one that does horizontal edge filter with stride 2. So it's a different approach in the algorithm, right? And look, you can see it's kind of giving you yet another filtered way. Same idea here. And that's it, right? So I only picked these. I mean, I could have picked 30 more filters, right? Edge detection, blurriness, whatever they are. But the key thing is that I want to point out, I had to give it these values originally. And then the operation is actually pretty consistent with what the CNN does. Now, another thing is, even though I write this in for loops, obviously, if you implemented a CNN like this, it would take forever to train. Remember that a lot of these operations get converted into matrix multiplications, okay? So that get that speed up. Got it? Any questions on CNNs? Probably half the questions on the exam will be on CNN, so. No questions? You sure? You get it? All right. This is important. So I want you to get the intuition more than anything. We'll look at the code, but because the code does abstract quite a bit, right? With Keras, we'll just create an object, it's a convolution, and that's it. But it'll have parameters. So I want you to understand that really you can think of it like this. There's a filter, there's an image, there's these for loops, and when you were learning how to iterate through two-dimensional arrays, you did the two for loops thing, and I'm sure you did some operations. Similar approach, except not in for loops, but matrix multiplication for the speed up. And also the CNN needs to learn these values. So initially they're going to be random. All right, so is this clear? No questions? All right, great. So like I said, the intuition in question I will ask you about, but I can definitely tell you I'm not going to ask you to filter an image on the exam or something. All right, so I show this kind of because I believe it's the best way to understand how the CNN works. All right, so now that we're done with that, so that's kind of the background on CNNs, we can start writing our CIFAR10 code, right? So that will obviously take a while. But that's kind of what we're doing this week. And then by the end of it, hopefully you guys will have a very powerful tool, CNNs. CNNs are not just for images. They can be any problem that you can convert into like a grid can in theory be solved by a CNN. But, you know, obviously images are pretty important. So let's go to the course repo. And under TensorFlow, CIFAR10. All right, so I'll start going. There's a lot, obviously, because we have to load the data and everything. I will copy some things from the GitHub so I don't have to type up everything. So let's go to neural nets here and stop me if you have any questions. Yeah, so here. All right, so it's the Keras CIFAR10 CNN. All right, great. So, all right, so we're going to go line by line, kind of laying this out. Just notice a couple of things. Like, I very easily just do this. CIFAR10, and boom, I have my X, Y, everything. But for your assignment, I really want you to go through the problem of, I have a folder full of images. Why? Because what if you, get hired to take a camera and go take some pictures and then do some machine learning? You're not going to have some convenient library to do this for you, right? So then you have to, so that's the problem that you have to address, okay? How do you start with a folder of images and process them? One recommendation though is get a library, get a data set and make sure that the size is the same. Now in the pre-trained model, the VGG that I showed you, that actually is not necessary anymore. You can just always take images of any size and just convert them to a specific size and process them. So that's why you can do it with any image. But here, because we're building this from scratch, dimensions still matter, okay? So definitely get a data set. Also, don't, if you have an image that's 4K or 8K, it's not gonna work, right? So there's a limit to this RAM, right? And so I would say images that are no bigger than 300 by 300, just so that, because you're all running on CPU, I assume, most of you at least. And so if you have a GPU, go ahead and run on a GPU. But here, CNNs start to get big. Images are certainly big. So unfortunately, this didn't take that long on my computer, I think. So should be fine. Okay. But at this point, now we're getting into something that can get big pretty quickly. Got it? All right, perfect. So let's go ahead and open the Jupyter Notebook. Yeah. All right, so let's open our Jupyter Notebook. So I'm just gonna go to the desktop. All right, so here we can go to an environment list. All right, so let's activate our environment. So I'm going to do conda activate CIFAR10 TensorFlow. Now I should mention that TensorFlow has, I guess this is referred to as the high-level API and the low-level API. As you might imagine, we are using the high-level API. That's Keras, very high level. However, today I believe I'm going to introduce, I don't know, I'm getting the classes mixed, but we may be using a lower level API. We'll see that. And the difference is that in the lower level API, yeah, I believe it's in this class. The lower level API is going to be a little bit different from the way that we've been coding up our neural nets, right? So what were we doing? Sequential, right? And then sequential, I think. That was the object that would allow us to add the dense layers, I think. Yeah. So I think this time around, we're not going to use that approach. And we're going to use actually an approach that I like more, which is a little slightly lower level API. Okay. Just means like how much you can get to the guts of things and be able to process. And that's good, actually, to be able to have a little bit more access, although it's a little bit more coding. All right, so we're in the environment now. So I'm going to do Jupyter Notebook. And like I said, I'm going to copy some code, but I'll describe it. Okay, so here we can just start a new Jupyter. Okay. All right, so I'm going to rename this. As I said, this is CIFAR10. It's the classic. So the classic for a long time was MNIST, and I think you guys did some homework assignments with MNIST, maybe? No? Did you not use MNIST? Doesn't matter. MNIST, the problem, CIFAR is like MNIST, with the only difference that it's not handwritten digits, it's animals and things, but also it's in color, and that's important, right? Because you want to be able to process the RGB. Those three channels make things difficult sometimes. All right, so CIFAR10, let's call it DNNs, because we will do a DNN, which is what you guys already know how to do, and then scale it up by throwing a CNN at it. Just not a pre-trained CNN, but instead just a from scratch CNN. All right, so we're going to copy. I already installed all these libraries, so you guys may be missing a few, okay? So I'll give you the commands, but yeah, basically CIFAR10 data set. I should say the CIFAR10 data set has 60,000 images for training, 10,000 images for testing, I believe, and 10 classes or so. Okay. All right, so copy this one. Okay. All right, so what are we importing here? We are importing NumPy, TensorFlow as TF, Matplotlib, Keras backend as K, and then Keras layers. And if you notice, now we have input, we have flatten, we have dense. You're probably familiar with some of these, but you're not familiar with the conv2D. All right, that is the convolution thing that I was talking about. All right, where the process now is that these filters will get run through these images, even though the filters are not initialized to proper values yet. But as we train on 60,000 images, what happens? The CNN now will have nice values in there. The better the values, obviously, the better. Okay. I'm also, to make this work, we're going to throw in some pretty advanced techniques, right? Something called batch normalization, a leaky ReLU. A leaky ReLU is just a ReLU where it doesn't give you 0 anymore. You see what I'm saying? It only gives you like what ReLU did, right? Any value above 0 is still the same, but any value that was 0 previously is now just a very tiny number. And that is because you don't want to multiply times 0 sometimes. Instead, you'd rather multiply times 0.00001, if that makes sense, just for the stability of the model. Otherwise, when you're multiplying times 0, sometimes the weights are actually getting destroyed. If you want to. So a lot of these tools, leaky ReLU, batch normalization, are for this, for stabilization of the model. Got it? All right. Like I said, this has a lot. All right. But it's because I'm taking you guys. Where were you? You were in XOR, right? So DNN's 2010. And now we're past 2012. 2012 is without these batch normalizations, but with it, it's beyond. Like you're 2015 or so. So pretty advanced now. So you're at the stage where this is now good, except for the pre-trained stuff. That's because that's different. All right. So dropout is another one. Dropout is pretty interesting. Also for stopping overfitting. And I'll mention some other applications for it as well, but it's kind of a neat thing that you can do. Instead of trying out multiple architectures, you just add dropout and it's equivalent to that in a sense. Okay. So there's a lot of stuff. Okay. So don't worry if it's like, it seems like I'm rushing through a lot of these things. Just be aware of them. And right, that this is the recipe that we're following. And a lot of machine learning sometimes, as I think I've said this before a couple of times, is a lot of, oh, my battery's not. Yeah. It's experimenting, right? So what I'm giving you with CIFAR10 here is because I already know it works, right? But you're going to do a homework assignment on this, where you're going to get a big data set of images of at least 3 or 4 classes. I would like it if you get more than 50,000 images for training, 10,000 for testing. Obviously, you don't have to collect these, right? Find a data set on Kaggle or somewhere like that of color images. But I'll try something different, I would recommend. And then basically, you may need to change things of the architecture. Got it? Any questions? All right, great. So, all right, so we have here from model, optimizers is going to be the atom optimizer. Okay. Which is like stochastic gradient descent, but just more stable as well. Why? And I keep saying stable, right? You might think, why am I throwing this? Well, the reason is we're making a CNN. A CNN is deeper. What that means is it's more layers. And the more layers you have in a model, you're taking a weight that's tiny, multiplying it times another, and you can see how it's going to start. It might destabilize a little bit. You see what I'm saying? I think one analogy I've heard is like you're carrying a stack of books, right? And then somehow somebody shoves you, and then the books don't fall down, but like a couple of books move to the left, right? Next time somebody pushes you, they move a little bit more to the left, and eventually, boom, they fall. You see what I'm saying? So think of that analogy if you want to think of what's happening to the weights. They kind of start going in some weird direction. And so these tools kind of help you to keep things like how you want it. Got it? Does that make sense, guys? All right. Anyway, we're going to go through it. As you can see, Keras has a really nice, well, 2 categorical. You've used this with the label encoder. We're just going to use 2 categorical now. And then, as I said, I'm just using from dataset CIFAR10, but you guys have to read from a folder. All right, so I'm going to run this one. Let's see if it runs for me. It's thinking. And you guys should also run this. Did it finish for any of you?
I ran 30 like 20 minutes.
Oh, did it?
Yeah.
Oh, you've ran everything already. Okay. Not sure why it's taking so long.
I didn't make that. I only just ran.
And it's finished already? Oh, there we go. Oh. Huh? But it seems like it ran, right? And the second time around should run pretty fast, I think. Yeah. All right, good. All right, so everyone should be here, hopefully. So you've got the libraries. I've explained that we're using a lot of these. Then the next thing is the number of classes. So like I said, there are 10 classes. Okay, for this example, we can take a look at those. But it's handy to have that as a number, so you can just run 10 classes, okay? Then, as you can see, I will just very conveniently load this data into my XTrain and XTest. So this is what usually you X and Y, then you split it, right? You'll have to do all of this, okay? And it's not trivial by any means. So I want to emphasize, but I think it's a good thing to do. You can use any library that allows you to get this done. Just keep in mind, put the classes per folder, right? So every class should be a folder. All right, so when I run this CIFAR10 load data, I should get XTrain, YTrain, XTest, YTest, and I kind of have something very consistent with what we have done before. Okay? Remember, it's the image and the label, the image and the label. So the labels are 0, 1, 2 through 9, and then the images are basically 32 by 32 by 3, because these are color images, so they have the RGB channels. Okay, all right, so it finished. Okay, so then you probably get something like downloaded from Toronto or something like that. Yeah. 30 more seconds. Yeah, so I had already done this, so. Did you guys finish? Yeah. All right. So now the next step is, and these two are really important for you to pay attention, okay? I've said many times, I think you've heard me, that you should always normalize your data, right? And that applies to everything in machine learning. Machine learning just learns better when the values are between -1 and +1. It's just like a thing, all right? And so you should always normalize your data. So in this case, we are going to normalize the images, right? So the images here are going to be in RGB, right? But every R, G, or B is in the range of 0 to 255, right? And so we don't want that. And so basically we're just gonna, there's a lot of ways to normalize, but this is just one way, just dividing it by 255, since we know the maximum value. Make sense? All right, so we're transforming. Now, do you do this on the labels? No, right? The labels just have 0, 1, all the way to 9. You only do this on the images because they have from 0 to 255. Any questions? All right. What is this one here? Two categorical just means that we're going to convert, kind of like we did before. And we specify the number of classes. So actually, let's move. This is one thing we probably want to take a look at. So I'm going to move it here. All right, and let's take a look at just one value, X test, 3 or something, or 2. Yeah. So let's run this, normalize it. And you can see the values are there, right? That's what the data looks like now normalized, okay? Now we're going to apply two categorical to the labels, but let's look at the labels before, right? So I'm going to do the same. Copy, just going to grab YTrain, and I'm going to grab the same 3, right? And just take a look at it. And this is an array of 4. Oh, no, sorry, that's 1. So there's only one value in there, right? The number that's in it. Okay, so then now we're gonna run it through two categorical with the number of classes, and we're gonna look at the shape again. So I'm just gonna copy this like that. What do you think happened? So I'm gonna do Y train 3, right? 3. What do you guys think? Make sense? Before, three, right? Oh, it's let me run it all. So I'll do this, this, and that. Okay, so let's take a look at it.
Do you do X train or X test? Sorry, that's.
You mean
Yeah, right there. Oh.
It didn't matter really. This one was just, I wanted to show you the data, what it looks like. I probably should have done it before the normalization, just so that you could see that it said like from 0 to 255. Does that make sense? All right, so this is actually pretty important stuff. This is the normalized version, but I want to show you the labels. So the first one here, I grab a sample of the Y's, the third one, and I print a shape. And it says 1. That means there's only one number in there. And what number is that? 4. That's the class. Let's say that class 4 is bird. You see that? But then if you notice, I do 2 categorical with num10 classes, right? I converted it like the label encoder, but the label encoder would take a word like the actual word car and convert it into a 3. Remember that in sklearn? Here we're doing something similar, but the input is already a number, 4. And I'm just converting it into something else, right? Which is what I want you to pay attention to, really important. So here, this is a vector, basically, of 1 with the value 4 in it. Do you guys see that? Whereas when I do this to categorical num classes and I print it again, it now is a vector of size 10. And the value of it is this one, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So why?
So each class or each number represented in Y train before we use the categorical was a number between 0 and 9, I think. Or 0, yeah, 0 and 9.
That's right, exactly. So basically it's because this is the 0, this is the 1, this is the 2, this is the 3, this is the 4. You see that? This is the 5, the 6, the 7, the 8, the 9. So now this is called one-hot encoding. Okay, very important that you get this. This is an important concept because it is the output of the neural network, the output layer. Remember that in the output layer, we are learning what? Categories, right? You guys see that? So probably I should do this on the whiteboard. So here, all this, although it seems like it's not important, it's really important to understand the neural network output layer. Oh, I need to connect. Oh, there we go. All right, so we're going to build a neural net, right? the neural net so far, we know it's going to look something like this, right? That's the image. It's 32 by 32 by 3. Then I'm saying to you guys that we're going to try out two models. We're going to try a DNN. You already know how to do this one from the XOR one. But someone had asked me last week, what's the easiest way to process an image? You flatten it. So we flatten this into a vector, which would be 32 by 32 by 3. Do you see that? Feed it into the DNN. Or we don't do that, and instead we feed it to a CNN, which doesn't require this to be flattened. It can take the cube, such as this, or actually the 4-dimensional tensor, because it's going to take batches of cubes. But we still have an output that's common to both. What did you learn when we were talking about, like, you know, the binary classification, right? We wanted to learn if this would be a 0 or a 1. Does that make sense? But now we have a multi-class problem, which means we have 10 neurons in the output layer. This is the output layer. So that means we have this, dot, this, and we have 10 of them, right? So we want a machine that does what? That for every neuron, it can predict values between 0 and 1. Do you see that? We need that. We need this machine to sometimes say this is a 0.5, this is a 0.7, this is a 0.1, this is a 0, this is a 1. But it predicts that. So randomly, it would do this, right? However, guys, however, as we start training, we're also going to provide the real data. And what do we want this data? If this is a bird, which is class 4, we actually don't want the numbers to be like that, right? One convenient way would be for it to say, if this is class, let's say that's class 4. So this would be, we want this to predict 0, or as close to 0 as possible. 0, as close to 1 as possible. Do you see that? And so that's why when we give it the real data, right, we give it the what is called a one-hot encoded version of it. Because really, these are going to be like 0.001, 0.1. This will probably say 97, something like that in a good model. They're not exactly the 0s and 1s, but that's what it gets better, obviously, when the numbers start looking more like this. That's because it means the weights are good and it's predicting. This is the ideal that we'll never achieve, but this is the ideal, the real data. And so that's why we can't do this if we just say 4. You see what I'm saying? Like if I give the model a 4, what is it going to learn? It's going to learn 4s. And because it can't learn a 4, it probably just say everything's a 1, right? Because that's all it can do. But if instead of giving it a 4, I give it this approach, then I have now a vector of 10, which is real, and the predicted vector of 10. And as I'm, learning, the model starts to look more like this, and then the errors are lower. And then now once I have a vector that looks like this, I just pick the index with the highest value, the index argmax. The index with the highest value is 4. Boom, done. You just predicted a bird, right? Got it, guys? All right, hopefully that made sense. So that's called one-hot encoding, very important. If you have language, for instance, and if you have a vocabulary of 65,000 words, you have 64,000 something zeros and a 1 for the word that you're learning. See, it's very powerful. All right, so let's keep going. So we have like a half an hour, so we can make some progress. Let's go back. Yeah, so we should be here, right? So I think we ran this one. Yeah. So we've converted the data to one hot encoding. We can also do Y train. So this is always, shape is something, believe it or not, when TensorFlow 1 came out, you couldn't even do shape. So this is definitely really great. So what does that tell you? You have 50,000 labels there that are one hot encoding. Would be a good idea actually to do this for all of them. So let me grab all of them. And we're going to do the shapes. So this is dot shape. Okay, you can see this is, there you go. 50,000 images, 32 by 32 by 3. Okay, this is important that you know this structure. PyTorch, I think, for instance, prefers the channels first, I want to say. So in a PyTorch, if you had images like this, you would have to flip them, right? You know, do a conversion so that you have 50,000 by 3 by 32 by 32. I think the batch is definitely always the first one. Okay, so it's always, you know, because this can be 1, this could be 50,000. It doesn't matter to the neural net. Okay, so yeah, so actually we don't need to print all of them. That's it. But now you know that's a tensor. That's where the name TensorFlow comes from, because it is a flow of these things, right? In our case, we're going to give it, we're not going to train in one shot, give it this tensor. It's probably too big. Instead, we're going to, but now batches. So we come back to this idea of batches. We're going to feed in a tensor of maybe 16 by 32 by 32 by 3, and so on. Okay, so we'll take a look at that. All right, so hopefully that made sense. So we printed the shapes here. And what is this? Let's train. Yeah, so this is just for image 54, right? If we go to that image, row 12, column 13, channel 1, so it's the blue channel, no, sorry, the red channel, R, that's the value that's in there. You guys understand that? You see what I'm saying? So we're just going into that we're going out of all the images, we're going to the 54th image. But the 54th image is 32 by 32 by 3. So in that cube, we're going to the row 12, column 13, but we still have 3 channels. So I have to pick, actually, it should be 0, 1, and 2, I think. So probably this is G, green. There's a number in there. That's it. All right, great. And this is not relevant. It's just, you know, us seeing things. Okay, so believe it or not, we're ready to go at this point. So now we're going to build the NN architecture, okay? So this is just taking from the XOR, except that it's going to be a little bit different, okay? So I'm actually going to type this one up to not go too fast. Okay, so I'm going to do here NN architecture. So this is the architecture that you already knew from XOR. Except that instead of writing it with NN sequential, we're going to take a slightly lower level API approach. What this does is it gives you a little bit more control of what's going on. In particular, you know, we have one function that produces a value that becomes the input to the next layer. The output of that becomes the input to the next layer, and so on. So notice the difference between this KNN and sorry, between this DNN and the one from XOR, and you'll see what I'm saying. It's a little bit more lower level API. All right, so we're gonna start with input layer, right? That's the input. All right, so in this case, we have something called input. And all we need to do is define, because this is going to feed into a CNN, we don't have to flatten it anymore. We can just, or actually, let me take that back. We do need to flatten it here. We don't need to flatten it in the CNN, okay? But we will flatten it here. And I'll explain to you why, okay? It's not like you have to flatten it in the math per se or the matrix multiplication, but you have to flatten it just because of the TensorFlow objects that we're using. Okay, so let's do, what's the size of an input? Just one input. 32 by 32 by 3. So this is a tuple of 3. All right, so now I have that. And now I need, the next layer would be, you can use X for all of these if you want. Or if it confuses you, use H1, which is hidden 1, and then the next one hidden 2. And then this is entirely up to you. I used to do the hidden 1, hidden 2, but it's better just to use X. All right, so if you do X, right, the next layer in the neural net is a dense layer, right? Exactly what you guys learned. So you have an input layer, dense, 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 output layer. That's exactly what we're doing, and we're going to draw this in a second. So a dense layer is a fully connected layer, which means all the neurons from one layer are connected to all the neurons of the other layer. So how many layers? What's the size of an image? 32 by 32 by 3. What size is that? Do you guys know? It's like 3,000 maybe, something like 36. All right, 3,072. That's the size of the vector if we spaghettify, right? Now we need to specify the size of the next of this layer, right? So what's the intuition? So if you remember in the past when we had like 4 inputs, we were always using like 10. But here, when you have something that's big already, we use a funnel type of an approach, which means every layer we make it a little bit smaller or smaller. Okay, that's kind of a best practice. So in this case, I'm going to say that the number of neurons is 200. Could I have said as 300? Sure. I could have said as 211, 212. I mean, 198. Right. So it's kind of experimental. That's where dropout, it's a little bit helpful sometimes, because dropout, in a sense, is like doing something like that. What if I tried 195 or 205 or 220? You see, dropout, as I'll describe later, breaks some connections as it's training. And so the network is basically every epoch learning something a little bit different. Okay. So I have here dense equal 200. Then we specify the activation. So in this case, what activation should we use? We can just use the ReLU, which is kind of where we are, right? We've talked about that one, ReLU. Okay, you see that? And then here's something that's different from the way that we did it before, right? Do you remember? We didn't do this, where we take the output from this operation and make it the input to this operation. Do you guys see that? So in this case, the input would be input layer. Oops, sorry. Got it? That's different. This is lower level API, which is more abstracted in the higher level API, but this gives you more control because you could do things to this input layer. For instance, let's say that in between, I want to do some processing to it. Now I can take input layer, do something, and pass it on. You see that? So it gives you that nice convenience of having the variable kind of outside, decoupled, if you will, from the neural net to process it. Now, the dense layer requires as an input a flat vector. Our vector is currently not flat. It is a cube, right? 32 by 32 by 3. So because dense requires, just because of the way it's written, we're going to then flatten it or spaghettify it, right? It's sometimes called. So we're going to flatten the vector. So I'm going to then throw in here x equal flatten, which you remember, we have this available. And I'm gonna say flatten is sorry, like this, and then here, right? So we flatten, we call the function flatten, and we provide us the input in, oops, should go to sign. Okay. And then in here, input layer, just like that. Yeah.
I think you said flatter.
Oh. Flatten. Yeah. So we have flatten here. And so now we take that, and now it goes from a cube spaghettified. Okay. But that's not like that we should do that necessarily, or that linear algebra can't process that. It is just a dense works that way. Okay. So that's the thing. Like I was saying with PyTorch, we just have to say maybe 3 by 32 by 32. They just have their own ways of doing it. And I actually like those consistencies sometimes. Okay, they force you to be. Got it? Everyone with me? All right. So now that we've done the flattening thing, we pass this to a layer of 200 with activation ReLU. Now this input layer obviously has changed, right? So now this is X. Now we can move on to the next layer in the neural network. You can keep doing this for as many layers as you want. I encourage you, in fact, for your homework to try multiple hidden layers. Maybe if you'll beat the CNN. I don't know. It could happen. That's up to you. All right. So then you do X and then another dense layer. This one, again, remember the funnel idea. Force it to learn with less. I always say this is like students. If I give you guys a month to do the homework, you'll rest for 3.5 weeks and then, right, do the homework. So you procrastinate. It's the same with a neural network. You don't want to give it, you want to force it every time to learn a little bit more. So that's kind of the idea here. So 150, activation is going to be ReLU. Again. And then the input to it is the previous one. So this is where I was saying in the past, people here would write hidden 1 and then hidden 2 to indicate the layers. I mean, it's good if that helps you. It's not necessary for the model, right? But for you, it might be a good. And then here, obviously, if this is hidden 1, then the input here to this one would have been hidden 1. But here is just X. Okay? And then finally, I'm only doing 2 hidden layers, so it's definitely a deep neural network. And I'm doing output layer now. And the output layer will be a dense layer also. What's the number of neurons here? Number of classes are 10, yeah, exactly. Because we have 10, right? Is what we were talking about, the one hot encoded thing that we talked about. So num underscore classes, comma, now we need an activation, probably. And then we have the input to it obviously is X, the previous X. So which activation and why? This is an exam type question, right? So which activation and why? Which activation function do we use and why? Huh? We only want, what's the one hot encoded look like? Zeros and ones. So we want a machine that can produce values between zeros and ones. Eventually it tends towards 0 or 1. Why? Is that all it does? So that would be a partial credit answer. You're missing a component there because sigmoid does the same. No, that they both 0 and 1. Sigmoid and softmax both produce 0 and 1. But there's a difference. What is it?
That should be something.
Huh?
Might be something. The probability down to 1.
Because the probabilities add up to 1. Very good. That is important, actually. We're going to go back to the whiteboard for this one. And to see what that means, you know, this is really important. So our vectors look like our output vectors, right? They're one hot encoded. So you guys have looked at them, actually. You definitely know they look like this, right? They definitely look like this. But if we don't do softmax, we could end up doing, and we get 0.3, 0.4, 0.2, 0.6, 0.5, 0.1. Do you see this? This is sigmoid. It gets you this. And then you could say, oh yeah, I picked the highest value, 0.6, but 0.6 and 0.5 are pretty close. Do you see what I'm saying? If you add these also, they do not add up to 1. So the softmax you want, now, can I ask you this? If you look at the one hot encoded vector, does it always add up to 1?
Yeah.
Yes, because everything's 0 except for the one that's a 1. So this meets the property that it always adds up to 1. So why not make this one always add up to 1? Before, to give it that little extra push. Because at the end of the day, the machine, as I said, here it predicts 0s and 1s. By giving it the softmax, it does so, but the differences are bigger, right? That's kind of what you're achieving. And so now this would become, since this was the highest, right? This, you know, I don't know, but a lot of 0.05s. And then here it's like 0.15, 0.5 maybe, right? So there's, but they add up to 1. And so it's a bigger separation, if you will. Yeah, go ahead.
What happens when there's a
Tie where?
like in the output?
There's, well, let me say it like this. Programmatically, argmax will return, if it's got 2 values that are exactly the same, it just picks the first one. So programmatically, it'll work like that. But it's very unlikely that you're going to have I mean, your weights should, if it's a good model, right? It should start to look like a lot of 0s and 1s, like 0.99s and a lot of 0.001s or something. But if you did get that tie from a programming point of view, I can tell you argmax will just, they're the 2 are the same, it just picks 0 index.
Yeah. And if you're getting that a lot, I mean, you probably
You got a bad model. I mean, you actually have so maybe throw a C in there. Right. All right. Yeah. So good answer, Abby. So yeah. So exactly. So it is a softmax allows for these to add up to 1 because these already add up to 1. Okay. All right. Great. So let's go back to the code. And like I said, we'll finish this code on Thursday. I'm pretty sure we're moving at a good pace. So now. Yeah, so we were doing the architecture. Oh, yeah, so the activation function then needs to be softmax. And you can see that it's still pretty easy, really, with TensorFlow. You can just say softmax here. That's it. Models pretty much, the architecture is defined. Now, it's always a good idea to have a model object. Remember that you guys will need to export this into the .h5 file, which is then converted into the TensorFlow JS files. So it's good to have the whole thing within this model object. So you can do model. And then here, the way it works is you just have to specify the input layer, comma, and the output layer. And then I'm missing it. Okay, that's it. The model architecture is defined. Now let's take a look at, so let's actually run it. Oh yeah, I see that. Okay, perfect. So it went through. Now, you always hear like GPT-4 has how many parameters? A trillion. Llama something has 7 billion parameters, right? That means the weights and all of that, right? So we want to see already this little architecture, how many weights it has, and compare it to the CNN. What do you guys think? Do you think the CNN will have more parameters or this one will have more parameters? We'll see. We'll see. But that's the great thing about this is that we can see, right? So we're going to go over here, the model summary. So this is similar to what we had done before. And it's got 646,260 parameters. That's all the weights that it has. Remember, it is 32 by 32 by 3. Imagine if it was 300 by 300 by 3. So now think if it was 4K. I have no idea how big something like that is, but and multiply by all the neurons. That's why you can't do 4K, 8K with neural nets. You have to always downsample it. I think like with a GPU is like 1,000 by 1,000, possibly. But that's as big as it can get. So you do lose some data. So as you can see, there are some limits with today's technology, and that's one of them. All right, so now that we have the summary, we can just, we can proceed to train. All right, so that we can definitely basically do the training of the neural net, right? Of the deep, this is a deep neural net, you should know that. So I'm gonna go ahead and, oh, you can see the 3072 there, right? That it got flattened, okay? So you had calculated. All right, so let's then, this I think is pretty similar to what we had done before. We're gonna do the, so create an optimizer as an atom optimizer, a learning rate of 0.0005. Then we are going to use a loss called the categorical cross entropy. Okay, so we have to get to this, right? This is one of those things where we're at the perceptron, we have to go to stochastic gradient descent, we have to use MSE, cross entropy, and then categorical cross entropy. They're not as difficult as they sound. All right, and basically there's really just like 2 or 3. So another one called RMS prop, I think, but they're basically just words you use, at least in Keras, okay? But basically, we will learn how this kind of works, the equations for this, and then just keep in mind it says categorical. I believe there's a binary one also when you just have a 2-class problem, okay? But this is the categorical cross entropy. The optimizer is opt, this one over here, and accuracy, although you know how to add more metrics. Got it? Any questions? All right, so let's go ahead. The learning rate is, remember, something that you can play with to figure out, you know, what's the best learning rate. And then now we can take a look at the fitting process. So I'll go over some of the variables. All right, so I'm gonna let it run. Can't remember how long it took, but so what do we provide to fit? We provide X train and Y train for training, batch size 32. Remember, we have 50,000 images, but we do not want to provide a tensor that is 50,000 by 32 by 32 by 3. That's pretty big. And so we might run out of RAM. I mean, play with it, you know, see what happens. Instead, we usually provide batches. So it's basically 32 images, another 32 images, another 32 images, and so on. This is how you do it. And believe it or not, in a GPU, I usually just do 16 or 32 in the GPU. So it's not like if you have a GPU that you can somehow give it 50,000, right? There's still, but the processing gets, you know, like what I'm saying is, even when you give 32 with some problems, the CPU might take an hour, right? But if you give it 32 on a GPU, it takes 10 minutes or 5. So that's kind of how it works, okay? But in general, the batch sizes are small, although they can get as high as 256. but they're usually not that big. Okay. It's good to give batches because it's not a good idea to give a model just one. You know what I mean? And then another. It's better to give it several and it gets like, you know, several perspectives of the data. So that's always a good idea. Epochs just means the number of times we give it the entire data set. That's an exam type question. What's an epoch? Describe how it works. Remember, you're giving it all the data in batches. And also notice this flag here, shuffle means what? Every epoch, right? So every epoch, shuffle the data set and then give it 32, 32, 32, 32. Epoch 2, shuffle it in another randomized way, 32, 32, 32, 32. Third epoch, shuffle it, 32, 32, 32. That's also a good idea. Okay? And so it's still running. So what do we see here? What are the things to look at? The loss. What should be happening to this loss? Should be going down. What about the accuracy? What should happen to the accuracy? Going up. Is that what's happening here? So 185, 166 to 140. So it's gone down a bit. Accuracy from 0.33 to 0.50. Is that great accuracy? What would you expect for the accuracy to be? 100, right? That's what you want. Now, it's a 10 class problem. So this is another exam type question. Would it be better to, it's 50% accuracy, which is pretty bad at this point. Would you agree that the accuracy at 50% is bad? So maybe I ask you in the question, would it just be better at this point just to flip a coin? Would that provide, would a system that's just a black box with somebody inside flipping coins, would that be better? There's 10 categories, right? So you can't really flip a coin, right? It's more like flipping a die, a 10-sided die. But you get the analogy, right? So what probability does a 10-sided die give you? 1/10. This gives you 50. So which one is better? The random. So my point is, I worded this badly. Should you do it randomly or should you trust the classifier? Classifier, right? So the classifier is better than the. So it's my point. This is not random. Okay. You see that? Maybe a better analogy is like when flipping a coin, it's a binary. So in that case, maybe I give you that question. The accuracy is 60%. It's a binary problem. Is it better to flip a coin or is it better to trust the classifier that does 60%? Why?
It's better 10%.
Yeah. What's the probability of the flipping the coin? 50-50. You see that? So my point is there is a lower bound to all machine learning models, randomness. Binary, flip a coin, 50%. So if you try to sell me something that is a classifier and you're telling me it does 40%, I'm better off inventing some gadget that just flips a coin and it's a much better classifier. In the case of 10, a much better, some contraption that gives me a 10-sided die. It's better, randomly speaking. So this is better because it's 50%, so it's not 10% accuracy. Any questions on that? Clear for everyone? Okay, so let me know if you have any doubts. This is then so it finished, right? And what do you guys say? We threw out a deep learning, right? Aren't you sad? So you hear all this hype about deep learning and 50% accuracy. Uh-oh. So it didn't do a good job. So you're kind of now in 2012, the ImageNet competition. right? And in that competition, people were trying, I'm sure, neural networks at the time, but they just weren't trying, but they weren't succeeding. Okay, they basically weren't succeeding. So, yeah, so we have quite a bit actually to evaluate and visualize. So it's almost 10 times. So we'll pick up here on Thursday, but I just want to kind of tell you where you are right now, right? So you're kind of at ImageNet competition in 2012. People do have some architectures like this, and they're getting about 0.50. And then comes in AlexNet from University of Toronto. They're going to throw a CNN at it, and we're going to see what happens. Does that make sense? All right, so yeah, we'll pick up here Thursday, and then we got to visualize some of the results also, so of this approach. But we'll continue this or finish it up with CNNs on Thursday. All right, so we'll stop here for today, and yeah, I'll see you Thursday.